All right, we'll start. Good morning, everyone. Welcome to the very first expert lecture series of Colorado. It's great to see such a good turnout, and looks like we are not as underground as we are supposed to be. So, a little bit of humor there. But just in case of emergency, safety things first. You have doors behind you. Follow the exit sign. It will take you directly to the muster point, which is in the north surface log. Now I would request everyone to take their smartphones out and scan this QR code real quick. It's not a bad link. It's just a promotional stuff. I promise. Nothing bad. Yeah. If you want to take my photo, that's fine as well. All right, moving ahead. So I would like to acknowledge the team of Geo-Institute, the ASCE Colorado section. So if you see any of these faces at lunch today, say a big hi to them, as they have been very kind in supporting this event. And a big thanks to Becky Umlin, Hunter White, and Nicholas Chipolati, who have been helping me setting up. As a good host, I'd like to thank our sponsors, even sponsor Kiewit, gold sponsor Night Be Sold, and Terracon, the bronze sponsor. I would like to thank Cage for supporting us. All right, without any further delay, I would like to invite my colleague, Mr. Martin Walker, to introduce the speaker of the day.
Got it. Yeah. Thank you, Shahbaz. That should work. Hi, everybody. It's quite an honor for me, I feel, to introduce Professor Hashash for this talk, the inaugural talk of the ASCE Geo-Institute Expert Lecture Series here in Colorado. I have to call myself an excited user of AI, an excited geotechnical engineer for sure, but and perhaps I have a little bit of programming intuition in my blood from my family, but I am certainly not a regular user of it. And as such, I asked AI to create these slides, and this is the product that I got. And so you'll see that it comes with some flaws, and it comes with not quite exactly the right stuff. But nevertheless, I put it up just to demonstrate exactly that. But it was also quite successful at boiling down some of the things that I asked it to do. So with that, I'd like to just quickly go over Professor Hashash's professional background. He is a professor and Granger Chair at UIUC, University of Illinois at Urbana-Champaign. He got his PhD, master's, and bachelor's at MIT in Boston. He's a leader in geotechnical earthquake engineering and many other aspects of civil engineering in general, and he is an ASCE fellow. I asked AI to align the various aspects of Professor Hashash's career and credentials with the Kiewit values of professionalism, integrity, excellence, and stewardship. And so it gave me a little P next to the ASCE fellow mark with professionalism. So job well done there. Major technical contributions. This is on the excellence category. He's the founder and lead developer of Deep Soil. And I'd like to point out here a little bit of stewardship, where Deep Soil is now RS Seismic. He has passed on Deep Soil, and so that the community can continue to develop the good work that he has initiated. He's the author of over 100 peer-reviewed publications. That's a tremendous amount of effort, and certainly contributing to the excellence of the society. And an international leader, certainly in seismic and underground engineering. We still call it let's do the Hashash whenever we're trying to evaluate racking in an underground structure. So, and then I'd like to just point out some of the recognition and leadership. National Academy of Engineering in 2022. That's a huge deal. And if you look at the colleagues that he was inducted with, he's quite a younger member of that cohort. So congratulations on that again. Certainly a fellow of the ASCE, past president of the Geo-Institute, and from personal experience, he has been an SME and peer reviewer on many infrastructure projects that I've been lucky enough to be involved in, and I certainly thank you for the mentorship on all of that. So as part of that, he has never compromised on the integrity that he has shown to make sure that the product is delivered right, and that the the sliding scale of all of the allocation of funds at the end of the day is as reasonably equitable as possible. And so that's stewardship and mentorship. He's a longtime mentor to students and professionals, including myself. Developer of widely adopted research tools, not just deep soil and iSoil and so on and so forth. And he has given a lasting impact on education and engineering practice, and he's not done yet, as you'll see here. Just a quick recap of our agenda. The lecture begins right now with some Q&A in about an hour's time. Lunch will then proceed, and please feel free to use that time for more Q&A with Professor Hashash. It's a valuable time. Track him down and don't let him eat. Well, he can eat in the car on the way to the airport. The program concludes promptly at 1:30 for aforementioned dash to the airport. Please welcome me in joining, or please join me in welcoming Professor Youssef Hashash for this great talk.
Thank you so much, Martin. And thank you, everyone. Let's see. There are a few technical things I'm going to do. Can you hear me fine through the system? Pardon? Yeah. I need to now share the couple of more buttons. Are we doing well? Okay. Well, thank you, Shahbaz. Thank you, Martin. Thank you, Geo-Institute, Colorado chapter, Denver section, for having me. And thank you all for taking time from your busy schedules on a Monday of all days and to be here with me. I almost did not make it. My flight was canceled, rescheduled for today. Managed to hop on an earlier flight, middle aisle, back of the plane, still made it, so I'm good here. So I'm going to share with you my thoughts, my experiences, and my views on AI. Some of them, those of you who know me, are deliberately provocative, just sort of so that we can have a good conversation. And as Martin said, we're not going to end the Q&A exactly at 12:30 or 12:35. Till 1:30, we can keep on having a good conversation. So it's okay, we'll eat at the airport. We were talking about lounge food, so probably eat at the lounge. So with that, I'm going to talk to you about AI and machine learning in geotechnical engineering, history and transformative opportunities. Now, you may think that I picked this topic because I was hopping on the latest bandwagon. I've been doing AI for 15 to 20 years when people were telling me, this is black box, no one will use it. So maybe it's a little bit different. We have a different perspective. Of course, the good stuff is done by the students. Things you don't like, it's my fault. Okay, I'll take responsibility for it. Just been blessed with a tremendous number of students. Also, my earliest involvement in it was also thanks to Professor Jamshid Ghabousi, a pioneer in the space, but not many of you might have heard of him. So here's my outline. We may kind of deviate a little bit. Talked about data in geotechnical engineering. It all starts and ends with data. So we should keep that in mind. We'll talk about AI tools, introduce a little bit the framework and AI in civil engineering. It is not new. I'll give you some selected applications for tunneling, strut loads, for surrogate modeling, extracting underlying behaviors, sort of think about bringing in the physical world. Talk about generative AI, some intro into the future, and some additional final concluding thoughts. And I'll try to do all of that in the allotted time. So, role of data in geotechnical engineering. I'm kind of focusing on geotech because I'm a geotech engineer This is a Geo-Institute, but I also think of myself as a civil engineer, also as an engineer in general. So I know a little bit beyond geotech, but I'll try to kind of speak mostly on geotech stuff. So we are dealing with the engineering of geologic material, earthen material, nature, what nature gives us. Earthen materials have complex properties, high variability, nonlinearity, anisotropy. And the first thing we try to do is we do our investigation and we try to develop a picture of what's out there. We try to develop a ground model. And this is why engineering geology is very important for us. It's an integral part of our discipline, but it's all dependent on data. And our challenge is not a lot of data. We can never have enough data, right? Now, thinking about the modern discipline of geotechnical engineering, airborne mechanics, which is the work that Carter Zaghi introduced, kind of brought in ushered the era of modern geotechnical engineering. He cleverly took the law of buoyancy, for example, flipped it, and you got the effective stress principle. Interesting. That's what it is, by the way. The effective stress principle is actually Archimedes' principle, just in a little bit different way. Took a basic concept, look at it in a different angle. And of course, worked on many, many spaces. In fact, Carter Zaghi worked in soil mechanics, rock mechanics, lab testing, and theoretical. He has the book Theoretical Soil Mechanics. So the focus of his is to extract information, data from the tools available to him at the time. Question for us is, can we extract something more fundamental in terms of behavior from modern laboratory data, from modern equipment, and data processing techniques? The other thing we do is we very much say, you hire an engineer, you send them out to the field, right? Because that's where you're really, really going to learn about something. Going back to the observational method, which was described in 1969 by Peck, it really all started with the work at the Chicago subway, and of course that's where University of Illinois comes into play. There they established a clear relationship between the excavation support system and the observed deformations, sort of physical world and the response of structures. Now, if we look at the tools throughout modern geotechnical history, we can go back to 1900 for remote sensing, pigeons with cameras. Of course, now when we think about remote sensing, it's something completely different. It's PT, triaxial test, CPT, now Internet of Things. We have INSAR, LiDAR, many tools are available to us. Now, parallel with that, we have tools that we use and we develop to interpret and extract meaning out of the data. Simple graphics, this is like, our plasticity chart, finite element method, going back to 67, personal computers, spreadsheets. Wow, spreadsheets really solve lots of problems. Nowadays, we're dealing with neural networks, and we'll spend a bit more time on that. So if we think about our discipline, which is an empirical discipline, is heavily an empirical discipline, it's what we call nowadays is shallow machine learning. It's correlation between variables. And here I threw up on the slide is just some of the ones that we use. Some of them we still use today in our work. But our limited data, which enough to plot on a graph, has evolved into big data. We are able to capture, save, observe massive amounts of data, almost in a near real-time, near continuous fashion. The data availability has changed. Instead of dealing with a few hundred data points, we're now a few million or even upward of billions of data points. The tools, the data availability has changed, so shouldn't the tools we use change as well? Let's talk about AI. Give you a bit of a historical perspective. AI in civil engineering and tools, past, present, future. I'm not very good at predicting the future, but I'll speculate. So the inception of artificial intelligence can be traced back to Alan Turing. If you haven't seen the movie about Alan, please watch it. Brilliant, brilliant individual. Brought in a paper in psychology and philosophy about computing machinery and intelligence. This is 1950. Introduced the Turing test, a method for evaluating whether machines can think. No machine has come close to passing the Turing test. Well, we'll see. What we want is a machine that can learn from experience. And we as geotechnical engineers, as civil engineers, experience is very important for us. What if we can have that machine experience captured? So instead of having experience of one individual, hundreds, if not thousands of individuals and multiple generations. So if we look at the early days of AI, and in the 1960s, work on artificial intelligence and structural design, although it is not now possible to develop a comprehensive, adaptive structural design system, there are many indications the major developments in the next few years, change years with decades, will be in this direction. We're there now. 1986, survey of the state of the art of, at the time was known X systems in civil engineering. Army Corps of Engineers would say, indicated a long-term commitment to research and development of expert systems. But really in the mid-80s into the early 90s, that whole discipline kind of died or kind of went into a, see, I can't call it died because it's, of course, has been revived extensively. In 1991, I consider one of my main mentors in this space, Professor Jamshid Ghabousi, introduced the idea that you can use artificial neural networks, and I'll explain those a little bit more in a sec, can be used to represent material behavior. Is actually was a brilliant moment of thinking about, wow, I can represent it with a neural network. This is a complete shift from conventional elasticity, plasticity, classical mechanics behavior. So, or approach to constitutive modeling. So AI, as you know, as we know, is, iRobot, 1950. In my era, when I was in college, we would watch The Terminator. And then, of course, Star Wars, drone wars, which are real now. And then, of course, these various assistants. And, I can't fit enough. There isn't enough space to put in the various efforts right now being put in various AI tools. Generative AI is one type of AI. So let's talk about what is artificial intelligence. And this is helpful terminology from Rome 2021. Artificial intelligence, the science and engineering of making intelligent machines, 1956. And of course, I talked about Turing's as well. You can use it for planning, build control algorithms that will enable an agent to synthesize a course of action that will achieve its goal. Some of what you do with the TBM, tunnel boring machines, is actually planning, a form of AI. Natural language processing, very important, so that you can actually interpret and turn it into actions. Machine learning, and we can talk about shallow and deep machine learning. And there are many, many different aspects. So we need to think about AI is not ChatGPT. It's not just ChatGPT. There's Claude or Grok. It's a lot more than that. So where it all started, people were amazed that with all the conventional mechanics and mathematics we had, we were nowhere near the ability of a brain to do things. Watch a child learn language, actually learn multiple languages fluently in the first few years of life. us as we age, it becomes much, much harder for us, right? Or watch a child from whatever the child is to crawling, walking, running, and doing all kinds of fine, gross and fine motor skills. Brain is an amazing thing. And so it was very inspiring to people to study the brain and try to build things that look like the brain or networks to that. And that led to the development of artificial neural networks. They are modeled, inspired by human biology of the brain. There's neural networks, multi-layer structure. All inputs are connected to all layers, called multi-layer perceptron. And then you have deep neural networks. Now you'd have multiple hidden layers. The classic thing is you have an input and an output, and then you have hidden layers helping you develop the connectivity, the connections. And here you have every node connected to every other node. Now, as you start scaling this up, it turns out you run into a limitation, having all of these connected to all of them. So while we start with this classical neural network, then additional ones started developing. There is a convolutional neural network. There is recurrent neural network for sequence in time, graph neural networks, so grid-based, sequence-based, graph-based neural networks. But the problem is you can't keep on building larger and larger networks whereby you can have all nodes connected to all nodes. And so large sequences of data are common, whether you have textbooks, time series, etc. Prior architectures struggle with very long sequence data. You would end up having to have something very, very large. And so therefore, the breakthrough came by developing the self-attention architecture, whereby you can actually remember everything before as opposed to just a little bit what happened before. So that had a major implication, major breakthrough. And by the way, simplifying it greatly, just to kind of help you on recognize why we had this sudden, as if things, the floodgates opened in that space, the self-attention layers. And that led to large language models that prior to self-attention, it was generally infeasible to have context language. Go back to a landmark paper, 2017, attention is all you need. And the new model architecture called Transformer is based on self-attention. And then you have ChatGPT. And while we talk a lot about text and word sequence, but actually we can use that same kind of architecture to work with very large data, such as tunnel boring data, and geotechnical surrogate modeling that I'm going to describe a little bit later. These are applications done in my own research group. There are also other applications that have been done. I'm going to focus on things we have done because it's just lots of things. Now, things you have now, we're getting into agents. There's a personal AI agent, almost like your own assistant. You might have heard about OpenClaw. It's an open source AI agent powered by LLMs. It's very powerful, but it's extremely unsafe to use. So don't install it by itself because someone could potentially hack into your system and cause all kinds of damage. But nevertheless, Jensen Huang, someone knows a little bit about this space, says refer to OpenClaw as probably the single most important release of software, he says probably ever. NVIDIA recently just released NemoClaw. It's an open source stack on top of OpenClaw for privacy and security, adds guardrails to enable enterprise use. So we're going to see a lot of changes with these things. These are very, very recent, and they're going to make a lot of, the impact will be there. LLMs will eventually potentially become almost like utilities or commodities. It's what we use these LLMs for is where the added value. So let's talk about now, I'm going to step back, show you simpler applications, and then build up, and then leave you with some thoughts about the topic. So I'll talk to you about selected AI applications in geotechnical engineering. I'm going to talk about tunnel-induced ground response and strut load and temperature analysis for deep excavations. Those of you who might know, I enjoy working underground. And so these are things I learned about. The issue we have is in a typical urban tunneling project, we have these phenomenal machines called tunnel boring machines, fully instrumented, nearly fully automated. Some of the newer ones you can actually control from an app, by the way, and you can control every aspect of tunneling. And we are tunneling in ever more marginal ground and also heavily urbanized space whereby we cannot tolerate a lot of movement because of potential damage. So we're trying to control that. So we have a ton of data coming from these TBMs. Now, we had the fortune of, thanks to an NSF support, National Science Foundation. I think we started it in 2017 or 2018, I can't remember now. It took us many years till today, with partnership with the Los Angeles Metro. It's a part of a industry academia collaboration, whereby the kind folks at Los Angeles Metro gave us access to TBM data, all of instrumentation data for 3 lines, become 6 tunnels because they'd have twin tunnels for each. This is a subway that's being built in Los Angeles. And we had the Crenshaw line, the regional line, purple line. They changed names now for these, but this is when we started. So you have these tunnel boring machines. And when you look at the data for these, just to give you an example, for the ground movement, we have 3 million data points, and the TBM records 1 billion. And similarly, similar order for regional and purple line. I don't think you can put that in an Excel spreadsheet, can you? Now, we have 2 choices. One is to trim down, filter the data to have an interpretation, which, by the way, it's still important. Don't think that's not important. But are we leaving something on the table? Are we losing or not paying attention to additional knowledge? If we think of data as knowledge, then yes, the answer is yes, we're actually leaving a lot on the table. So how can we use all that data? Well, we have long sequence TBM operational data. We can leverage transformer attention, right? That's the breakthrough. And we create domain-specific TBM tunneling system tailored for the LA basin. So now it's to have the local experience, right? We talk a lot about it. I have 6 TBM tunnels and assist with predicting ground movements, estimating ground conditions, detecting ground heave, and potentially controlling TBM. I don't know if you've been hearing about physical AI and world models. This is what these things will be going in, the direction will be. So this is going into that dimension, because if I can use the TBM parameters to estimate ground motion, ground displacement, sorry. I was giving this morning a lecture on earthquakes, so that's why I use the term ground motion. I can do it in reverse. Say, here are my ground acceptable displacements. What should be my TBM control parameters, or what should I start adjusting? So I'm not going to go into the details of how we did all the training. This is going to be part of a paper that PhD student Wendy Zhao she's working on and finishing up. She's finishing up the last paper and defending soon. What we did is we would have in each one of these lines, we have 2 lines like northbound, southbound, or right, left, whichever one you call. We use the data from one, we learn the behavior from that, and look, estimate the other one. And this is what you're seeing. The data point, the dots are the actual data points. The bands are what our estimates are. And you can see we are able to capture not only maximum displacements, we are able to capture the shape of the displacement trough and the evolution of the displacement as the TBM is approaching. Now, I want you to also recognize the resolution of the displacement we're working in, 1 inch, less than 1 inch. We're actually at 0.2 to 0.3 inches. It's actually within the resolution of the measurements. So, but these are the requirements nowadays in urban areas. They want us to be at very, very high levels of resolution, and you need to use the requisite tool to do that. The other thing that you can do also, see if you can estimate ground conditions. If you're on the, whether you're on the engineering side or on the contractor side, everybody is interested in DSC, right? Differing site condition. And hence, you want to have tools that would hopefully tell you what's the ground ahead of you. Now, in a closed face, fully pressurized TBM, say, earth pressure balance machine, you really cannot see the ground. You get to see the muck and people start opining as to the ground. Well, it turns out there are other tools available, and we actually trained our neural network to also tell us about the ground. Now, you said, well, how did I check it? Well, we trained it with boreholes, and the way we estimated it, we compared it to what the engineers estimated the geology. And by the way, the engineers would not necessarily always be right. We found that actually, in many cases, we agreed, but in some cases, we disagreed. We had something different. But nevertheless, it's another way. So now I have, from a TBM data with the site investigation data, I have a tool that allows me to both estimate ground movements and ground condition. Shall we say the world is your oyster? So now you can start thinking of different ways of utilizing these tools. Now, we are here being hosted by Kiewit, who probably has lots of data on these things. And you can imagine Kiewit can decide to develop their own world model for TBMs, and that can do things like that. And there are also, of course, other contractors that can do the same thing, or everybody can work together and we would have a true world model, maybe. Now, thing we can do with these tools is we do these things called shapely additive explanation, SHAP. Let me put it this way. It tells you which parameters are important for the behavior. And here, when you look at it, it really gives us an understanding of what is controlling the movements, for example. We're looking here at the screw conveyor rotation speed. The foam line airflow, it turns out, makes a big difference. And it depends on which tunnel and what they were doing. And then normalized upper shield pressure. You see, it's pretty dominant. And we know pressurized face with bentonite around and then grouting behind, that's really how you guarantee minimal deformations. And we can see it. But also there are other factors that come into play when you don't do that all the time. So we see those dependencies. We can study them, we can understand them, and we can evaluate them. These parameters have been an issue of dispute between sometimes the contractors themselves, within the subs, and also contractors and the owners. So hopefully these kind of things can help us remove the mystique or the mystery around these issues and do a better job. So let's talk about something else, struts in an excavation. I'm just picking topics, okay? And we have done more topics that we don't have time to touch upon today. We know that when we put in struts in an excavation, that when they're exposed to sunlight, things can move. And if you don't do things properly with balers, I think, Martin, you remember some of those, you can be in real trouble. But we'll not touch upon that now, but we'll talk about estimating these extra thermal loads, and they can be substantial. Now, the thermal loads are continuous, and the way we see it is that this is an example. We picked a strut from somewhere. I'm not naming the projects. And you can see they actually sync with the temperature changes during the day. It's very clear. We've known it for a long time. This is nothing new. We've known it. It's nothing. Now, there's been many, many studies talking about how you estimate that thermal load. But if you look at those studies, in 2000, we were looking at 1 reading per day. In something we did in 2003, 4 readings a day, 2005, 1 reading per day, more recent, in 2015, not recent, it's 11 years ago, 24 readings per day. But on a project, Trans-Bay Transit Center, we had 96 readings per day. For the LA Metro, we had them as frequent as 500 readings per day. Okay? Our conventional tools no longer are able to do that. And for that, we actually use a recurrent neural network, which is designed specifically for series, time series. And through a lot of work, I'm not going to go through that, showing you here, let's talk about the top graphic here. Okay. Load versus time. The black line is what was measured, and black line here is the temperature. And you can see, it's changing, right? Even though, and by the way, this is during a period where we know there was no construction activity, no change in the excavation configuration, which means that at some point the load should stabilize, right? The earth load. Now, the kind of gold line here using a more linear regression type of approach, like the approaches of Fino, Hashash, Boone from that time. And you can see it's still not stabilizing, and you see lots of noise. But then once we brought in our recurrent neural network for the estimate of that, we go up and go straight. Those techniques that we found that we had developed before were suitable when we had infrequent data. But this high-frequency data, you cannot chase it that way and with these. And you can then establish relationships whereby we see that if you started putting in a strut on the hottest day, you will not see a lot of temperature load. But if you put it on the coldest day, and we actually preload a little bit the struts, then actually it experiences significant temperature loss because of the temperature. We know we can now use that data for something more meaningful and useful. So let's now talk about, many of you might have heard about surrogate modeling, and I'm going to give you an example of what we're doing it for discrete element simulations. This, as you know, soil particles or even boulders are this large discrete elements, and you can representing them as a continuum in a finite element doesn't always address a particular problem. So we go back to Kundal in 79, where it says, okay, let's model the individual particles and have dashpots and springs to represent the contact. And they are used in many applications, Mars rover, excavation dumping, conveyor, any type of large material handling, we use these techniques. The reality is particles are not spheres, the ones we deal with. And so really we would want to represent the soil more, or boulders or whatever particles you're dealing with more reliably or more faithfully by putting in polyhedral particles. The problem with those is issue of contact detection. Contact detection takes about 75% of the computation, and for polyhedral particles is an absolutely demanding computational part. And that slows things down, which means limits the application and the use of these particles. Now, before we got into the surrogate modeling, we had established ourselves a technique whereby we were able to hit a record polyhedral number of particles, 50 million on HPC machines. But one of the ideas was, can I replace this very, very computationally demanding contact detection with an artificial neural network, which, again, I'm not going to go through the details of it. And the question is whereby you train it once, and you can actually then estimate for a large number of problems. And the answer was, we actually finally had the breakthrough. I've been trying that for over 10, even maybe close to 15 years to try to replace the contact detection, but the technology wasn't ready. So here's a simulation of DM model versus a surrogate model, and you can see its particle flow looks pretty reasonable. And we had also quantitative metrics there by looking at the forces, boundary forces, and we found that it works well. The speed up was around 4 to 6 times, but what was more important is the reduction in memory. But also what's more interesting is that we could now put some of the calculations on a GPU. Before we had to do a lot of the calculation on a CPU because we needed to do double precision. This one GPU is actually can go single precision or even half a precision. So some of the precision in our calculations, we don't need them as much. So huge reduction in memory demands. And then we're now working on about simulations of 200 million particles, record numbers. so that we can then use it in more regular engineering work. Companies like John Deere, Caterpillar, etc., they use these techniques, by the way, for their simulations and for machine prototyping. Okay, so now let's talk about another application. And this is something we did way back, and we found that it actually falls very well with what we are thinking about these days, physical AI and connecting with the real world. How do we take our field instrumentation data and use it to extract underlying soil behavior so that then we can use it in forward prediction of conditions? That actually took us back. You always have to step back in time, go back to the fundamentals, and then move forward. If you go back to the concept of the feedback control theory, this is actually what enabled flight. Let's talk about maybe something we more are familiar with is cruise control, right? You have a controller, system, output, and goes back. And now, of course, we have adaptive cruise control. And those of you who have the latest Tesla with self-driving, wow, right? You can do some really, really cool stuff. But keep your hands on the steering wheel, okay? That is the feedback control theory. That is actually, the observational method is a form of feedback control theory. Keep that in mind. The same way we thought about, I mentioned to you effective stress principle. It's the inversion of the Archimedes principle. That's the same thing. So in engineering, we have design objectives. We do our site investigation, design, and then we go to construction. We acquire data. We store the data. We try to update our model, especially when the response is not consistent with our observation, make adjustment, and then go back. You see this loop? This is what we do all the time. Question is, can we automate it? Think about each one of these is an agent. That's the future, okay? I'll show you a little bit of semi-automation, but the future will be a lot more automation. Human will always be there in the loop, but we have more capabilities nowadays. So the way we did it at the time, we took the coupling of construction sequence and field measurements, and instead of doing one simulation and expecting the other result, we did two separate simulations, one with the construction sequence, one by imposing the measured displacements. We used one to extract stresses, the other one to extract strains. Stress strain is what? Soil model. We use that to train a soil model. We repeated that multiple times, so the model is evolving so that the two analyses give us the same result, because that's actually what we have. And you can do that. People were using, if you're familiar with optimization, whereby people change stiffness, etc. The problem is you cannot make a linear model nonlinear. This will make linear, will become nonlinear. It'll evolve to whatever it wants to do, and then you can use it to predict future excavations. Of course, we have now capabilities of capturing the construction sequence. This is LiDAR. We were the first to use LiDAR for excavations. It was 2006. Can you believe 20 years ago? That's how I feel old. We had, thanks to Professor Andrew Whittle, we had access to the data from the Stata Center at MIT, whereby we had both the construction history and the measurements. So this was our measurements of displacements, and we said, okay, so we're going to let the system, the self-learning simulation, start, and we assume first the behavior to be linear elastic, and then we kept on doing that process that I mentioned to you. It's called elastic initialization, and then we forgot. We told the neural network, forget elasticity, evolve as you wish. And then in terms of overall behavior, it actually captured it well. Now, we then compared that to measured data, and you can see here, I evolved from a linear elastic to a nonlinear behavior that's closer to what was measured. Now, people said, well, you have non-uniqueness, it's inverse problem, etc. Turns out the constraint here are so severe that actually you do not have that aspect of non-uniqueness. We tried it. We tried to break it many, many times. We couldn't. Okay, now let me pivot to generative AI because I still have more stuff to talk about. So we wrote a few years back, generative AI as a concept of the new geotechnical assistant, it was 1 page. If you're interested, just find it. There's the QR code. Whereby this is when ChatGPT first came out and we were trying a few things. So, of course, nowadays, it's all of you are using it. I still remember one time I went to an engineering firm, gave a talk, and the top folks says, "Oh, no, we don't use that because it's really bad." I said, "Okay, good." And I said, "Is it okay?" I asked the engineers who is using it, and there is no consequence to the engineers. They said, "That's okay." And they found that like 60% of their engineers were using it. So, so it's basically, it's part of it. And now I think the rate is much higher. ChatGPT, Gemini, I mean, many, many tools. But now they're getting far, far more sophisticated, more capable. But what we did is, I tried it on a few things. And I know some of your major organizations are working with this, whereby I just simply uploaded the data here and asked it to digest it and give me information, what it learned from it. And I used Notebook LM. I really like Notebook LM for technical stuff, by the way. And it just really provides tremendous summaries. And not only that, you see those gray thingies, you click on them, it tells you where it came from. Which means that you can import your own knowledge and use it there. Well, I had fun, and as you know, universities, we don't have lots of monies for TAs. So we said, okay, can we develop an AI teaching assistant? And that was actually not this last summer, the summer before. So this is before these things were easy. It took us about 2 months to develop it. The next one I developed, it took me 2 hours, by the way, versus 2 months. And we used Copilot Studio. We gave it the reference documents. And wow, it did a really, really good job. And so, this is it. You can click on it. The students could use it. But this whole age of AI teaching assistant is here. Okay, it's amazing. We have now at the university UI/UC chat, whereby it reads everything from you this, and it gives you citations, tells you this. So student tells you, asks you when is the exam, say. Go check out the teaching assistant. And of course, it relieves the load on the teaching assistant. We use it also for numerical modeling course. Now there's also far more broadly, more commercial. I think this one, just watch your ears. I think this one is video. I actually said there isn't, but there isn't. There is some. Let me see here. Okay. Okay, they are being, so geosim.ai. By the way, I don't have any stocks in these. I just picked ones that we are seeing. There's a lot coming up in the market, and I think eventually, of course, the market will filter things out. But what people are doing, they're trying to use geosim AI, to use AI for simulations as an assistant for compliance reviews, right? To make sure you are complying with whatever it is, code, environmental specs, etc. And it's doing, and the market is just exploding in many, many different spaces, in law, in medicine. And then there are now construction management assistants that are also popping up. And eventually there'll be few winners. That's how the market works. And they review submittals, quantity takeoffs, summarize specs. Drawing tools by Autodesk are coming up as well. So now let's go into the future. And so we're going to see a lot more domain-specific agents, like a geotech. And even within geotech, we have agent of agents that will connect things. But remember, at the end of the day, our job is to deliver an infrastructure solution. And so really, really, we need to make sure everybody is speaking to everybody else. Our AI agents will speak to each other. And so everybody uses them, puts them in, and then the agent of agents will tell, structural engineer, you're doing something here that is not consistent with the geotech. Talk to each other, maybe. Or vice versa. How do we develop these? That's actually the challenge for us. We're talking about using these large LLMs with your own domain knowledge or company-specific knowledge. We're now hearing about system AI, holistic end-to-end. Why? Because it's the delivery of an infrastructure solution, not a single predictive model, and integrated workflow. Workflow aspect is key here. You will always have a human in the loop. You want to have explainability. You have to have ethical considerations, regulatory adherence, and the role of engineer. Our role as engineers now to understand how these systems work and use them. These are really, really sophisticated calculators. In the 90s, the idea of using finite element tools in engineering was, oh, you know, we have our classic tools, let's use finite elements. I've had actually the same comment made by somebody. Oh, but we need to use finite element because these AI tools are new to us. Same conversation, different lingo. We have different tools. We just need to get used to them. There is a lot of more now discussion of physical AI, world foundational models, and the big players are pushing hard in it. And if you listen to the most recent keynote talk by Jensen Huang at the NVIDIA annual conference just a few weeks ago, it's a fascinating talk about what's going on in various domains. And there is also one of his buckets is AI engineering. So the big players are either looking for partners or they're looking to displace people. Remember what Uber did to the taxi business, okay? So it's all, by the way, what's the most valuable part in all of this? It's data and knowledge. The models will evolve, will change, the capabilities will change, it's data. So welcome to the new age of empiricism. We're seeing emerging world models. World models, the idea is, or the physical AI, eventually it translates into something physical. The classic thing people talk about is putting in what I would say robots, right? So that you connect it all the way and the robot executes it. Now you say we don't have robots. Are you sure? How about the TBMs? They are robots. They're very, very close to being fully autonomous. And so, all the big players are releasing their large models. So here's, world models are entering the built environment here, for example. So you can see some people are attempting that. So are we out of a job? Well, if you ask Gemini, I'm not expecting you to read it. It changes the engineer's job description, but not the need for human professional judgment and accountability. It changes. It might help you a little bit with the shortage in availability of engineers, but the engineer who is engineering is going to still be very much pivotal there. But what do we need our engineers to be good at? Know how to ask the right question. And guess what? This is not new, right? I mean, usually even in our practice, when we have a project, all of us have to ask the right question so that we can solve the right problem. Well, with prompt engineering, it's about that, and it has evolved a lot, and I think we're going to learn. Will we be making mistakes? Of course we'll be making mistakes. Like we never make mistakes before AI, right? So also recognize that there is hardware now that is coming in with AI native to it. For example, this particular laptop has an NPU, neural processing unit, so that Microsoft has their own little neural network that lives on this computer, and it speeds up my calculation. It does them all local and my queries. That's the future, and we're going to see a lot more of that. So also, modern construction hardware is actually seeing that. Autonomous Caterpillar is having these fully autonomous in-quarry applications. So we're talking about, this world model, physical AI, it's being connected completely to that. So you could imagine a future whereby you can actually run through an entire project virtually and see where the problems are in construction before you actually break ground, improve the design, and then go and execute. I would assume companies like the company is hosting us would probably be a pioneer in that space. Now, how do we build domain guardrails? Because there will always be concern about it. So we wrote a paper that's going to be published soon in Geostrata about risk of adopting generative AI, but actually is how to make a risk assessment to it. So we're trying, and this is being led by Professor Zenan Medina at Texas A&M. Another one was be looking at building domain type of controls is a paper by Professor Krishna Kumar, UT Austin, with the problem of lateral spreading, whereby he considered 4 constraints so that we can keep those guardrails. So what we need to do is step back, think what are the really, really important, significant guardrails, but we need to be careful not to over-constrain it. Because some things we think of as guardrails may actually be untrue, actually. Why? Because we now go back to basics. So, back to Carl Terzaghi. What is a geotech to do? From the book, The Engineer as an Artist by Dick Goodman, quote from Carl Terzaghi, all the modest achievements which I have to my credit can be described by a simple formula, guided by common sense and casual observations. I recognize, this is highlighted by me, I recognized weak points in traditional procedures and tried to make them less weak. Didn't say eliminate them, less weak. Sometimes I failed, but usually I succeeded. So, what are we to do? Maintain common human sense and identify room for improvement in our practice. Be innovative. Well, if nothing else, we can help build the AI infrastructure. The data center space is really, really just, it's taking over. A lot of our colleagues are busy building data centers. So we have a role in building the infrastructure, the physical infrastructure. Now, of course, there are ideas of putting them in orbit for natural cooling, infinite solar energy, etc., which I think is brilliant. We'll see how well it works. But that may really remove some of the stressors on resources. We have water, power, etc., because that's actually a serious concern for the communities. With that takes me to my conclusion. So, the tools of geotechnical engineering have changed drastically over the last century. But geotechnical engineering has always been data-driven. We're on the edge of a new age of empiricism. AI is improving many parts of geotechnical engineering. I show you examples of things we worked on. It's not just about a regression tool. It's a far more tool of bringing in insight, helping us to exercise better judgment. Deep learning models can predict geology, encounter geotunnelings from sensor data. We can have surrogate models in a variety of ways. Self-learning models, kind of really very helpful for the dawn of physical AI world models. Current generative AI models can perform very interesting engineering tasks, such as report writing. They do it better than a first year or a straight out of college engineer. Better. That I can tell you, which means that our starting engineers need to use these tools to learn and also work with mentors as well. They can analyze and compare documents. I experimented with numerical modeling tools. I was surprised how well it actually gained insight into the issues of the numerical analysis. Numerical analysis is one of my areas of expertise, so I know a lot. I knew what the answer is. I threw it in to ask it, what did it know? It turns out it can do a pretty good job. Successful engineers have always innovated and adopted the tools of their time. The AI revolution is no different. AI models make mistakes, and so do human engineers. I think all of us have seen it. Either ourselves, we've made mistakes, or seen some of our colleagues. Last one, as an educator, Do we need to change how we teach civil geotechnical engineering? Do we need to talk to ABET? You probably know from my rhetorical answer question where I stand on that. And to end it, thanks to Pawan Kumar, who is a musician and a geotechnical engineer at Arrow, he asked Grok, I think, write a song about earthquakes in the style of Pink Floyd. And there you go. By the way, if you prefer Shakespeare, it will do that for you as well. So thank you, Pawan, for that. And thank you, and happy to take any questions. Thank you.
I'll put a chair for you for the Q&A.
Sure.
We'll start with the question. Mic in front of you. So if you can rotate it, if someone has a question, start.
Thank you so much. Are you sitting next to me? Okay, I'll bring you one. Okay. And I think we have space for online, right, folks? Okay, here you go. There is a, here? Yes, by all means.
Hi. There's a lot of uncertainty in engineering, a lot of surprises too, right? And Claude Shannon, who famous information guy in the early 50s, when he was tinkering with computer circuits, came up with the theories on information certainty. How, and a lot of the loss functions in AI are based on entropy. How do you look at uncertainty in a more probabilistic way? I know these models underlying, but when you look at decision trees and stuff, they're essentially Bayesian. And as engineers, we're not particularly thrilled with probability. How do you? I think one of the things we could do better is to better understand our priors, better understand our data. One of the things we suffer from with data right now is there's absolutely no standard for organizing data. So you can just get this mishmash of all these different data sources. So as an industry, infrastructure needs to come up and abide by certain data standards. It just can't be this ad hoc world of everybody else's formats. But back to my original question, how do you think engineers need to have the tools to deal with some of the inherent surprises and uncertainties that we encounter?
Yeah, I'll try to touch upon, you hear me fine? Yeah, okay. I'll try to touch upon several points you have. I'll just briefly about data and mishmash of data. For the LA Metro, it took us 3 years to actually harmonize the data. It was very, very challenging. Not because someone didn't do what they were supposed to, just how we structured it, we didn't do it well. In terms of data standards, I think we need to be very careful with that because we sometimes tend to think about it as if no one is dealing with that, with the type of data that we are dealing with. It turns out other disciplines have far more complex data sets and they've done it well, but we end up lagging. And soon we'll be having Professor Kumar and I write a paper about dealing with issues of geotechnical data standards. So because of this issue we're talking about. But let's talk about uncertainty. What is interesting that many things when we teach, let's go back to our educational system. We talk about uncertainty, but we do not teach our students how to handle it. And some of it is quantitative and some of it is qualitative, right? So there is part of it is in our educational, bring it up. And it's not just in yet another statistics course. It's actually how you use it in real world, day in, day out. Did you notice when I showed you the from settlements? I didn't give you a single point. I gave you a band. That's from the fancy neural network. So we can have that, we can integrate it, and then we can even bring it far more to the front because the data has noise and uncertainty, and we can transparently bring it all the way through. We need to do more of that because sometimes we get too fixated on a level of resolution that is unwarranted by the data itself. So very important for us to bring it in. And I work a lot with colleagues who, even before the AI stuff, about this, and we're trying to bring it. You saw the paper with Bayesian. We're trying to bring that into the neural network, and this is working with, I don't know if you know Professor Greg Becker in Maryland. He's a pioneer in that space. So we're trying to bring these back to the forefront so that we accept that. Because uncertainty is inherent. We just do not quantify it as much. You know, bringing in concepts of geostatistics. So. Sure, quick.
So managers are probably the worst at dealing with uncertainty. I think sometimes engineers understand the range of what they're dealing with, but when it comes up the chain to stakeholders and project managers that have financial stakes in the project, the uncertainty becomes something they don't want to hear much about.
You're right. At the same time, we always have reserves, either by, say, the contractor or the owner. You have to have a bucket of reserve, and that is inherently uncertainty. Also, insurance companies should be very interested in that. I think as we move towards things like these world models or physical AI type of models, it's not just about all the technical stuff. It's all the other commercial risk, regulatory aspects. They have become so onerous that they're actually sometimes preventing us from delivering infrastructure. If we bring that in within these models so that it's we can far more quickly get the number or something that we can present. I see that as a really promising way to get out from the trap we find ourselves in.
Next question.
Oh, and then okay.
Okay.
This
Arash.
Yeah, we'll start here and then we'll go there.
Okay.
Yes, go ahead. Is this going to be? We somehow lost the audio.
Is this going to be published?
Can you help me understand what do you mean by published? Will the lecture be available online, you mean? Or do you want me to, is my talk going to be in a paper that's published?
Either online or in a Geo-Institute publication?
So this is maybe the 10th or 12th iteration of this talk that I started it in 2023. And every year I've changed things. For this one, I changed dramatically some stuff, especially the concepts of world models, and I continue to do that. The presentation itself, after I clear out a few pieces out of it, because the students haven't finished their PhD, will be made available. I do not know how the Geo-Institute, I will provide you a PDF of it. The lecture itself, I don't know what you're planning on. I mean, I don't have a problem being available. I just don't know, how do you deal with it?
So we'll have a watermark PDF shared to the attendees. It will not be available to everyone, just the people who attended it.
Just the attendees.
Yes,
right?
yeah. It's just for the exclusivity of the presentation and also this series. So yeah, definitely reach out to me if you don't receive your email, but that's something in the process. Okay, next question.
So for a day-to-day like tasks of an engineer, if I look at that like a 2016, like an everyday life of a geotech is not that much different than what we do now. And I think I was an intern in 2016. So now I'm assuming that that's going to change like in 10-year time. So how would you say, like as a geotech or civil engineer or engineering construction, how would that be different, and in what direction should we train ourselves to be successful? Because I personally have an internal resistance to automate stuff. I mean, like, I like Excel the best. Like, I want to go like, and I want to see the calculations. And in Kiewit, we do a lot of hand calcs because we want to see the basics, and then we go to the modeling, and just because you don't know what happens in a model. And with this AI coming out, so how would you say, because I'm assuming like the slope of changes is way steeper than the last 10 years. And how do we set up ourselves for success and to help this speed up our industry and reduce the errors?
Sure. What I'm going to share with you is my own thoughts on this topic, and not, something that others may disagree with, and that's okay. We want to have all the ideas out here. If we look at the fundamental structure of our curriculum, because that's where it started, right? When you said when you were an intern, it actually hasn't substantially changed in the last 30, 40, 50 years. Fundamentally, it's about the same. Even with the advances we've made, put AI on the side, with numerical modeling, 3D modeling, etc., we're still teaching about the same. But those companies that can solve the more complex problems with these advanced tools end up actually sometimes having an edge. At the same time, I want you to observe the differential between the pay of a geotechnical engineer and the pay of people in computer science, in whatever computer science is. When I graduated, maybe it was 10, 20%. Now it is 200 to 500%. If you believe in market forces and how the market values your expertise, you realize that you're actually losing. Okay? The fact that the salary is so, and worse, sometimes geotech are sometimes the lowest amongst all civil as well, even though we deal with the highest risk. Okay? So that should get you thinking about it, is that, in terms of the broader market, they may say, well, geotech engineers are so inexpensive, I'm not using the word cheap, inexpensive, that we'll just keep it, because there's not a lot of money to make out of it. But of course, if you lose also, people are not coming into geotechnical engineering, then there's a problem. And guess what? We're seeing that. Okay? So the market hopefully will correct a little bit. But also, this is why I bring up the issue of Uber and the taxi business. Taxis were very, very low margin businesses, right? You would have never thought that someone could extract more value out of it. But the experience was less than optimal, to put it mildly. You order a taxi, it may come in an hour or 2 hours, right? And if you're somewhere off the beaten path, good luck getting one. Uber saw a technology solution to the problem and really severely displaced the taxi. And suddenly people overnight lost the value of their medallion, right? I wondered if something like that would happen to us as geotech engineers, in the space where it's just simply a procedural aspect. There will always be space for high-end, specialized, unique applications. But for the more routine things, maybe some of that could be replaced. So I take a look at it from the issue of workforce, the fact that we don't have enough coming in for a variety of factors. I think that's we start thinking about it. But also I see a role for the big players, where the money really is. The money is in construction, not in design. Okay? And also, there is greater reward there. In engineering is that the monies are low and the liability is massive, right? So I see that it's people who might lead these kind of efforts would be the big construction firms, because when you optimize a process, suddenly you save millions of dollars, gives you a more competitive bid, or you have a bigger bonus at the end of that year. So I see it, and why also? Because contractors are really integrating the solution. And how many RFIs contractors issue saying to the engineers, oh, by the way, did you see that this does not fit this? Right? I mean, we see that all the time, right? It's just the nature of how we're arranged as an industry. So I see us facing this, but also even as an individual, even if you were like a small shop geotechnical engineer, guess what? With these tools, you can do way more than you would have done, and that gives you a competitive advantage as well. My message is, learn these tools, try to learn, keep your solid engineering knowledge, leverage it to enhance your productivity and improve yourself. But then goes the whole issue of, do I still charge per hour? That's another question.
Thank you.
That's a good question. We have another question.
Yes.
Give me a second.
Thanks. Great lecture, and really got me thinking.
By the way, if you can get closer to the mic, please.
In terms of geotechnical engineering companies and trying to set yourself up on the right path, or set your company up on the right path for implementing AI in a way that keeps you on the forefront and keeps you competitive, what would you say? How would you go about approaching that? And I guess a more simpler question, what would you say are the top maybe top 3 AI tools that could be implemented today by an geotechnical engineering company?
Okay. It all really depends on the size of the firm. But let's think of, sort of a mid-size kind of geotechnical firm. The first thing I would do is that I would make issue an all points bulletin to my staff, the engineers, the support staff, etc. Say, look, we want to embrace AI, and please share with me your best ideas, your best practices, and how we can improve the processes. You will be surprised how many good ideas. Why do I say this? In academia, I'll give you the parallel in academia. The first reaction of the faculty was cheating. That's the first reaction. I was like, oh, okay. It's like saying when the students first came, the calculator was invented, that, oh my gosh, you didn't look at the log tables. No, it's not. It's the new tool. So I still remember very clearly when I told 105 students that in this class, we will be using various AI tools available to enhance this. All what I wanted them to say, just simply at the end, put a statement, what they used and how they used it, and bigger assignments to show the prompts they have used. At the end of that first lecture, the student came and tells me, oh, you mean it's okay to use AI? I said, no. You must use AI, okay? These things I've also noticed in companies nowadays is the reluctance, especially the top managers, is that our data will leak, it's unreliable, it hallucinates. Why? Because they see those headlines. Yes, they do hallucinate, as if the engineers don't hallucinate. I mean, come on. It depends on what they drank the night before or something. So I think it's more requires from the top saying, we are going to embrace it, but we want you to recognize it would leak data, et cetera, et cetera. So let's use tools whereby we have at least so that we can keep it within. That's the first thing I would do. And they actually will tell you what are the top 2 and 3. But one of the things I can tell you, one is issue of synthesis of data. 2 is that initial drafts of reports. It can give you a way to develop. Because, for example, you know how many companies have a template and then the young people don't know how to use it? And you just simply use this and with this. So a lot of these, and then you can start building up to building agents that enhance your processes. I wouldn't do that from day one. Build confidence and add. Build confidence and add and become routine part. At this stage, there is so much excitement and fascinating developments in different spaces that things are changing. I wouldn't say this tool versus that. You're here. ChatGPT today, Claude, this. You need to be very, very worried about data leak. Okay, there is no doubt in my mind. So that's where you need to have the right. And many of these, by the way, there are versions that are open source, meaning you can host them locally on your servers so that you can only work with your data. And you just need to update them. So maybe you're a version behind a little bit with the open source. And this is where what I mentioned about OpenClaw and NemoClaw. I wouldn't use them, by the way. They're not safe yet, in my opinion, because you need them to be deployed. You hear a few disasters, they fix it, and then you can be ready for that. But there are a lot of tools. Even something as simple as Copilot within the Office 365. It has capabilities that improves things, like very quick grammar check of your email before it goes out. It does an okay job. And it'll make mistakes. But also things like, you use things like Notebook LM. It's phenomenal. In terms of from a technical point of view, precision, it's amazing. Grok, Claude, the latest version of Claude. So they're changing, evolving. So I cannot say one tool. Say just stay tuned, but don't stay tuned and be on the sidelines. Engage. I recognize there are resources, etc., but invest a little bit of resources, not a lot. And you may decide, maybe many of the engineers are reluctant within that firm, then pick a few engineers who say, you know what, we like to be part of that experiment. And then learn from it. And things will evolve.
Press the green button.
So in one of your slides, you asked AI whether AI can take civil engineer job. And as a response was because of professional engineering judgment, no. Can you tell what is a special thing about professional judgment that AI cannot reach in 5, 10, or 20 years later?
Oh, I didn't say that. Okay.
Then it will take the.
So certain AI engines say yes. It says no. Actually, it says not yet. That's what actually the response was. Not yet. And I think you need to take that very seriously. Mm-hmm. Okay. Remember that there are companies that are well resourced are trying to build bases on the moon and on Mars. And all that construction will be robotic. What is there to say not bring that technology back to Earth? That's how the not yet there, okay? We started in spaces and in environments whereby, hopefully I don't have lunar lawyers to worry about, and there wouldn't be an injury, right? It's just a robot that something happens to it. So there is going to be, we need to do some serious soul searching about what is it? What is professional judgment? It's like a lot of times you go and you have a conversation with some contractor, or not contractor as a contractor, I mean an engineer, and you ask them, especially geotech says, well, based on my opinion or my experience, and we know that's, sometimes it's good, but sometimes it's not. It's just simply an opinion, right? Well, this will start filtering these out. And so it will start to creep into what we conventionally call professional engineering judgment. However, when you look at it objectively, oh no, it's not. So we'll have to redefine it, I think. And that's where you saw my thing about ABET and also the other professional engineering societies. I think we need to be prepared for it. The companies, these big companies, are not waiting. Trust me. They're moving all in. The startups that are working in AI and engineering, they're just going to it. I may have had people call me up just when a young 20-year-old person, never been to a civil engineering school, trying to solve civil engineering problem in these startups. There's money. And guess what? If they can hack around it, why not? Right?
Just follow-up question, sorry. As a follow-up, do you see a future that machine learning, especially neural network, based on the paper that you showed, will take the mechanical model, take over the mechanical model that we have already?
Oh, yeah. Yes. No, that we know it can do. We've already established it. Yes. Because after all, remember, a mechanical model is a very procedural thing. It can learn it.
Yeah.
Yes. And we've done it.
So I'm taking this one question, which is online.
Oh, okay. Yeah.
So,
And hello, our friends online.
okay. So he says it's more like an observation. So he's asking, is there any way to remove the black box effect of AI? And can we have the agents that actually analyze the LLM and make it transparent and actually reveal what it does and how it arrives at the answer?
The answer is yes. It's not a black box. And the more you query, you look at the architecture of these, you look under, you can see what's going on, where the information is coming from, etc. We just haven't built yet the tools to bring it up. But this, I expect that, and this is part of how I think it'll gain wider acceptance.
Okay. I'll just take one more question if anyone has. Okay, the gentleman on the right. Last question.
In the examples of the tunnel bore and the thermal data that you're using for modeling, you have hundreds of millions or at least several hundred measurements a day. What would you consider the sort of minimum bar for data density to usefully predict anything? Do you have an idea of a minimum floor?
Okay, Martin is reminding me of a conversation. So I had a student a while back. I was on that student's committee, and the student was very excited about AI and listed everything conventionally last chapter. I'm going to use AI. But I knew, and I asked the student, how many data points do you have? And the student said 3. I said, you can do linear regression. Okay. Now, actually, the question you're asking raises this bigger issue about, actually, with the online question,
Yeah.
is what space in terms of possibility is the data has filled? Because there is an issue of, let's call it interpolation of existing knowledge versus extrapolation. And the extrapolation without constraints can lead to really interesting answers. So what's going to be incumbent upon us is, as we increase our data sets, to develop the tools to tell us what part of the space we have. And therefore, when I query my AI models, it would tell me, yes, what you're trying to do is within the realm of knowledge, and therefore I'm going to give you this answer, or I'm going to give you this answer, but this is outside of, or at the edge, or I'm really, really far, which, by the way, goes back to, it will tell you, I mean, actually, by the way, this information is available, it's just we haven't done it. I showed you a little bit about the surrogate modeling I was working on as my student was preparing his paper on that. I said, I don't see the data space. Let's plot it. He found that actually he had deficiency in his data space. And there are tools, by the way, to do that, visual tools, so that we can easily understand it, because we're dealing with a multi-dimensional space when you deal with these data, right? TBM, I have 30 TBM readings. Actually, there are many more. And so think of it as that's 30-dimensional space, right? So yes, we need tools that would tell us that you are in a safe space to give a good answer, or now you're out on a limb. The same way when someone says, well, my experience says this, She said, well, since when, how many of these did you build? None. You know that this person is, okay, maybe someone has some good judgment, but they're way out that they maybe could be wrong, right? Same thing for people. It's just we now can formalize it.
Thank you for your response, Dr. Hashash. Very quickly, I'll be inviting a few folks to honor Speaker of the Day. David Meyer, on behalf of Kiewit, can you please come? Aaron Leopold from Region 7 ASCE Governor, he's here, so be good. Murtaza from ASCE Denver Branch, can you come? Murtaza, yeah. Mahfouz, can you do the honors of taking the photos? Thank you.
Thank you so much. Appreciate it. Elena. Okay. Thank you so much. Okay, I'm going here. Okay. And how about you? Okay, so
Big round of applause.
let me.
You can. From ASCE,
Oh, well, thank you so much.
and that's from Kiewit.
Oh my, thank you so much.
Yeah.
Appreciate it.
Yeah, we got your bags filled.
Oh, okay. I'm glad I have some space in my bags. But thank you so much. I really appreciate it.
All right, moving ahead really quick. Sorry, we're behind the schedule. Few upcoming events. So we're gonna have Dr. Carlos Santamarina in this hall. It's a Monday again, sorry about that. May 18th. The last one in the series would be Dr. Zikos. We are still finalizing the date. At the end of the year, we're gonna have the biannual conference, the Rocky Mountain Conference. It's gonna be on November 6th, so stay tuned for that. And since I already got you all forced up to sign up for the LinkedIn updates, you'll see everything happening. So thank you for joining us today. It was great to see everyone here. And please proceed out to have lunch. And there are lunch boxes, so if you wanna drive and take it home, that's totally fine. But thank you all. It was amazing to see you all.